In this video, I'd like to continue the discussion that we had on different types of nuclear processes that are going to lead to a more stable nucleus. So in the first video, I discussed alpha decay and beta decay, or alpha and beta emission. And in this one, I want to talk about positron emission and electron capture, all of which are strategies that nuclei can use in order to get to a more stable state, a more lower energy stable configuration. That's what we say when we say that they want to do something, right? It's anthropomorphizing a little bit, but it's really about getting to the lowest energy possible. So let's talk about positrons because they're pretty wacky. So a positron, which is sometimes symbolized by a Greek beta with a positive sign there as a superscript, is a positively charged electron, which just right there, it should break your brain because you've spent your whole life, at least your whole scientific life, understanding that electrons have negative charges, and that's a defining feature of an electron. And I'm saying, well, there's these electrons that have positively charged options also, and we call them positrons. They are the antimatter of an electron. So they're antimatter electrons, which is also kind of a wacky concept in and of itself, and they occur when a proton becomes a neutron. So if in kind of the configuration of the nucleus, it's needing more neutrons, it has too many positively charged particles, then a proton can become a neutron to help balance that out a little bit. And when it does that, it's going to emit a positively charged electron, which again, just wacky on multiple levels here. So let's take technetium as an example. So here's technetium 95. Technetium is one of those weird ones that is actually never stable. It's all unstable all the time. It's always radioactive, but it is below that 82, below lead. So it's in the transition metals, kind of right in the middle. So when it emits a positron, which is a positively charged electron, then let's kind of think about what's happening here. If I have a proton and it's becoming a neutron, so again, using my nuclide symbols here to show kind of, it's not the chemistry, which is what I'm used to saying when I'm talking about a chemical reaction, but it's showing the process that these particles are undergoing. And when they do that, in order to balance this thing out, I need to have a 0 in terms of my number of nucleons, my mass number here, and I have a +1 here below. So it's still an electron, but that electron is positively charged, so it's the antimatter to my electron, which is the positron. So this is what's happening to my technetium. Too many protons, need to get a neutron. We eject this guy now, positively 1. And again, sometimes this thing is written with the actual symbol, so you'll see it like this sometimes as well. They mean the same thing. And when this happens, then my mass number stays the same, right? I'm going from a proton to a neutron, which functionally have the same mass. I mean, of course, they're slightly different, depends on the precision, depends on the application, if that really matters or not. And then 1 plus whatever this is has to give me 43, so that would be 42. And if I look at my periodic table, so here's technetium right here in the middle. If I go down to 42, then I'm down at molybdenum. Little Molly. So again, the mass number stays the same, but I have 1 fewer protons. So functionally, what I've done here is I've decreased the number of protons and I've increased the number of neutrons, which again, with the region of stability or band of stability, if you fall on one side or the other, then one of the ways that you can do that is by messing with the composition of your nucleus in order to get back into that region of stability. And as you're messing with this composition, as these things are transitioning from one to another, then they're spitting out particles, or they're spitting out groups of particles, and that's causing it to shift into, to move into that more stable range. Okay, let's look at another example. Let's look at aluminum. It's weird to think of aluminum as a nuclear material, but there are radioactive isotopes of aluminum. Hopefully not in our tinfoil. All right, so here's aluminum 25. Isn't it funny that we call it tinfoil? It's not tin. At least most of it isn't. If we emit that positron, then to balance that out, my mass number stays the same, right? Because that's the key there. And then 1 plus whatever this is has to give me 13. So that means that it's 12 if we go to our periodic table. Here's our aluminum. We're going down to 12. That means we're going to magnesium. And that's a very stable isotope of magnesium, pretty common one. Okay, so that's positron emission. So we're emitting a positively charged electron when a proton becomes a neutron. And that's going to give us a more stable configuration because we're decreasing our Z, our atomic number, and we're increasing kind of those particles that are the glue that help to hold together those positively charged protons. Okay, let's talk a little bit about electron capture. Maybe I can even do this on the same page. So electron capture, I'm just going to kind of abbreviate with an EC. That's the way that you see that often. Electron capture is kind of wacky. Actually, all the nuclear processes are, which is why I like them. I just think it's kind of fun. So our unstable nucleus captures an electron. And these electrons are coming from the inner shell. So if we're visualizing the Bohr model of the atom here, which we always do, right? Because we're scientists. We're always thinking about what things look like. I was using diagrams. So we have kind of, here's our first shell, here's my second shell, here's my third shell, here's my Bohr model, my nucleus at the center. If I have some electrons in my inner shell here, then one of these gets slooped into the nucleus, right? The nucleus sucks in one of those electrons, which just sounds crazy because it is. And then when that happens, that electron converts a proton into a neutron. Oops. Because if I have a negative charge that gets sucked in, that negative and the positive charge then are going to cancel each other out and become a neutron, which again is just kind of wacky. So if we're thinking about this in terms of nuclide symbols, the proton and the electron, here's my captured electron from that inner shell that bashes into my proton, and then we convert to a neutron here. Here's my 0. Okay, and again, I'm balanced out across the board because I have here's my 1 proton. So it's kind of like a non-opposite 1 proton, gives me a 0. And then here's my my number of nucleons here is 1 across the board because of my electron is not 1. Okay, so when I add these together, when I suck in this guy to the nucleus, then this has all sorts of wacky implications. But let's just think functionally about what this looks like. So let's take potassium, for example. So potassium-40 is a radioactive isotope of potassium. There's actually radioactive potassium in bananas, right? That's one of the things that we think of as high in potassium. And so it has a slight amount of radioactivity in it, which means that we're slightly radioactive when we eat bananas, which is kind of neat. So when that potassium sucks in one of these electrons, which I'll put now just kind of on the other side, it doesn't really matter where you put it. So I take in one of these inner shells, I add it to this guy, then what I end up with here is my mass number is 40, so my mass number stays the same, and then the -1 plus my 19 gives me 40 as a mass number, 18 as an atomic number. So I started with potassium here, and now I'm down at argon, which is one of my noble gases. Which, as you would imagine, is a pretty stable configuration for this, because our noble gases are, while they have the potential to be radioactive and unstable like everything else, they tend to be more on the inert side. Now, you hopefully are asking at this point, well, what the heck happens to the other electrons? Like, we've been focusing now on the nucleus in our nuclear chemistry, but if I have an atom and there are electrons in it in a normal way, right? If there's a bunch of electrons in there in the shells, in the way that we think about them, you know, and orbitals, and they occupy 3-dimensional space and they have energy associated with them, then if I suck one into the nucleus, that has to have some implications here, right? So there has to be some sort of implication on the fact that this one's gone all of a sudden. because it's doing nuclear chemistry and converting something into something else. So what happens to the electrons? Well, there's a void then. There should be an electron here. There isn't an electron here. So now these outer shell electrons, these upper shell higher energy electrons, are all going to rearrange. They're going to kind of relax down into the place of that electron. So that void that was filled here. So we have this void now where the electron was, where it got sucked into the nucleus. Then the outer shell or upper electrons are going to rearrange and relax down. When electrons relax down, as we've learned in past videos and past information, electrons relax down, that energy has to go somewhere, right? It's a higher energy value going to a lower energy value. Well, that energy has to get released somehow. So there's my energy leaving. And usually it's in the form of an X-ray. So when we've talked before about electrons relaxing back down and excited electrons, usually that means that we're thinking about light that's getting emitted in the visible range. And so we've talked about the visible spectrum and the atomic spectrum. But when these guys relax back down, because of all the chaos there is here, we have to rearrange, reorganize. Then if this one gets sucked back down, these other ones have to get sucked back down. So we're just kind of rearranging and getting down to a new ground state. Then usually an X-ray is what's emitted here. So in electron capture, there's a couple different things going on that are important. One, the proton becomes a neutron. So functionally, we're again decreasing the number of protons. This is why I like to do these two together, because they both have functionally the same features, right? I'm decreasing the number of protons, increasing the number of neutrons, but they're doing it kind of in two different ways. In one of them, they're sucking an electron in, and in the other one, they're spinning a positively charged electron out. And when electron capture occurs, then X-rays are also emitted, which can be very dangerous, of course. Okay, so that's positron emission and electron capture. One other way, or two other ways, that have the same kind of functionality here to get to a more stable nucleus and a more stable configuration.